This video addresses the question of why do cells have to be small? So as we grow, we all start out as a single cell. We start out as a zygote, which is just a fertilized egg. But over time, that fertilized egg, that zygote, goes through mitosis and starts making more and more cells. So instead of a human becoming just one big cell, instead we're made up of trillions of smaller cells. And so this explains why that needs to happen and why it would not be possible for us to be made of just one big cell. So when it comes to cells and the reason why they have to be small, it really has to do with these two characteristics of a 3D object. And those characteristics are surface area and volume. So the surface area is how much area or space there is on the surface. So if we were to look at this box in the middle here, the surface area would be like how much wrapping paper you would need in order to cover all sides of the box. The volume is how much space there is contained within that 3D object. So that would be how much you could fit into the box to fill it up. To calculate the surface area, we can take the length of one side times the length of another side. So in this case, we could take 3 centimeters times 3 centimeters, and that would give us the area of one side of the box. Now a box has 6 sides, so we have to take that number and multiply it by 6. So to get our final answer, 3 times 3 is 9 times 6 gives us an answer of 54 centimeters squared for the surface area of this box that has a length on each side of 3 centimeters. Now for the volume, we have to take the length of one side times the length of another side times the length of the third side. So we usually express this as length times width times height. So in this case, we would just take 3 centimeters times 3 centimeters times 3 centimeters. So we would get 3 times 3 is equal to 9 times 3, which gives us a volume of 27 centimeters cubed. Now the exponential on the unit tells us something here. So the surface area is a squared function, whereas the volume is cubed. And what this means is that as the volume increases, it's increasing faster than the surface area. So if we were to take a box that is 4 centimeters on each side, you would have an increase in volume disproportionate to the increase in surface area. So the increase in volume would actually be more than the increase in surface area. And that starts to pose a problem when you're talking about things like cells, because cells can only get things like nutrients through diffusion, and the diffusion has to occur across the surface area of the cell. So let's see what happens when we take a cube and we cut it up into smaller cubes. So the second picture here, we're looking at a cube that overall has the same dimensions of the first cube that we looked at, so 3 centimeters on each side. But now we've taken this big cube and we've cut it down into smaller cubes, which is what we see on the third block at the bottom of the picture. And you'll notice that I wrote times 27, and that's because we can count the boxes or the smaller cubes that we formed from this larger cube. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we've got 3 rows of that. So I took 9 boxes times 3 rows deep in order to get 27 of these 1 centimeter boxes. So now let's take a look at the surface area and the volume of our new boxes that we've taken by cutting down this big box into 27 smaller boxes. So to calculate the surface area, we'll take the length times the width of one side. So that will be 1 times 1. And then because it's a cube, we have 6 sides, which gives us 6. So 1 times 1 gives us 1 times 6. So our answer is 6 centimeters squared. But we have 27 of these boxes now. So we'll take that number times 27 for an overall surface area of 27 of these boxes equal to 162 centimeters squared. So this is our new surface area of these 1 centimeter cubed boxes, but this is the surface area for all 27 of them. Now we can take a look at the volume, and once again we can still take length times width times height, which for a 1 centimeter cube would just be 1 times 1 times 1, which gives us a volume of just 1 centimeter cubed. But we have 27 of those cubes, so we take that number times 27. So we ultimately end up with an overall volume of 27 of these cubes equal to 27 centimeters cubed. Now you'll notice that our volume is the same because we didn't increase the size of it. We actually just took something big and cut it up into smaller pieces. So we didn't change the overall volume of this three-dimensional shape. We just took the volume and divided it up into smaller pieces. But when we compare the surface area, we have significantly increased the amount of surface area for that same amount of volume. So with the bigger box up here, we could look at something called the surface area to volume ratio. So we have a surface area of 54 centimeters squared, and that is related to or relative to a volume of 27 centimeters cubed. Now we can reduce this ratio kind of like we're reducing a fraction. And so 27 goes into 54 2 times. So we can reduce this to a 2-to-1 ratio. And what this means is that for every 1 unit of volume, we have 2 units of surface area. Now, if we look at the example at the bottom where we've taken this large cube and we've cut it down into smaller pieces, we've altered the surface area but not the volume. So now the new ratio is 162 centimeters squared relative to our 27 centimeters cubed. And once again, we can reduce that ratio just like we can reduce a fraction, which reduces it to, or changes it to, a surface area to volume ratio of 6-to-1. And if we compare these two numbers right here, we can see that the smaller boxes gives us a higher amount or more surface area per unit of volume compared to our one large box. So this higher surface area to volume ratio allows more surface area for nutrients to get into the cell. So the takeaway is that as the size of a three-dimensional object increases, the surface area to volume ratio decreases, which means there is less surface area for things like diffusion to occur. And so the flip of that is that smaller sized objects, so smaller things like cells, so smaller objects have more surface area per unit volume, which allows for faster and more efficient diffusion. Now this concept also applies to something like dissolving something. So you can imagine if you have a big piece of candy and you put it in your mouth and you're sucking on it, you have enzymes in your saliva that are going to be digesting and breaking down that candy. Now if you've got like a big peppermint and you're sucking on it, it's going to take a while because it only has the surface area of the candy to work on, and so it's got to work from the outside in to get to the middle of the candy to break it down and dissolve it. But if you put an identical piece of candy in your mouth and you chew on it, then what you're doing is you're not changing the volume because you've got the same amount of candy that you put in your mouth, but you're increasing the surface area available for those enzymes to work on. Another thing to note is that cells are not all perfect spheres or boxes. So we typically, when we're first teaching about cells, we kind of draw them as these circles and we say, oh, here's a cell. And it kind of falsely leads people to believe that all cells in the body are just these kind of perfect spheres. But in reality, cells come in different shapes, and the shape really has a lot to do with the function of the cell. So there are some cells that are pretty round. But there are also some cells that might be long and skinny. For example, there are some cells that are called squamous epithelium that tend to be kind of long and skinny. Also, some muscle cells are kind of long and skinny like this as well. We can have some cells like neurons. So some neurons in the body that can be over 1 meter long, which is over 3 feet long. So that's a really big cell, and that might seem contradictory to what we just learned, which is that cells have to be small. But we'll talk about why neurons can be really long in a second. This cell down here has things called villi. And some cells actually have microvilli, which is where on top of the villi, there are actually even smaller villi present. We typically see cells like this in the intestines, and that's because the intestines need to have a lot of surface area because that's where you absorb most of the water and nutrients from your food. So it needs to have a lot of surface area for nutrient absorption. So these different shapes allow cells to be bigger while not having to worry about the surface area to volume ratio as much. So for example, if we come back up and look at the squamous epithelium or these muscle cells or whatever these kind of long skinny cells are that are in the body, you'll notice that the middle of the cell is not that far from an edge. And in doing so, it means that all parts of the cell can get nutrients through diffusion pretty quickly and easily. And so the cell can actually increase its surface area without increasing its volume as much as if it were a perfect sphere or a cube. Same thing with neurons, is that no part of the neuron is very big. So they're these kind of like long, skinny cells, and they have these cellular extensions. So once again, as nutrients are trying to get into the cell and get into all parts of the cell, they can get to the middle of the cell pretty quickly and efficiently. And so by having this kind of long, skinny shape with these cellular extensions, it can increase its surface area without having the same amount of volume increase. Same thing with these kind of intestinal cells that I introduced down here. The cells can increase their surface area without increasing their volume at the same rate that they would if they were perfectly spherical or cubical. So the key takeaway here is that these different shapes allow cells to increase their surface area without significantly increasing their volume. So remember, it's all about surface area. We need to have more surface area so nutrients can diffuse, but we want to do that without increasing the volume. So we need to keep the volume either small or make sure that all parts of the cell have a close kind of relationship to the edge of the cell so that it can get nutrients.